Now, yesterday, the first report about what it's doing closest to the sun came out. These are instruments that are capable of looking very close to the sun. And it was realized that, in fact, the object is brightening. It becomes very bright right now as it comes close to the sun, and it's turning blue. And the color blue is very surprising because if there is any dust shed off a natural nucleus of a comet, the dust would make it red. And usually the surface of the object is at least an order of magnitude cooler than the surface of the sun. But what the new data indicates is that the object is bluer than the sun. How is that possible?
This morning, we have a report that the object got much brighter than expected, and moreover, the color of the object is bluer than the sun. And that's very surprising because usually when there is dust around an object, it should make it red. I should also say that the news yesterday was that this object came closest to the sun, and it received a huge amount of heat from the sun. And the latest report indicates that it became extremely bright, much more than expected for familiar comets.
There are moments in human history when the impossible becomes inevitable, when the dreams that once lived in the margins of fiction step into the light of reality. For over a century, the speed of light was that sacred boundary, the wall separating imagination from destiny. It was the universe's speed limit, guarded by equations so flawless and absolute that defiance seemed like lunacy. And yet, on an ordinary Tuesday morning in a quiet NASA facility, that wall fell, not with thunder, but with a whisper. No explosions, no cheers, just the soft hum of machines and the stunned silence of discovery. What followed was disbelief, then awe, the realization that humanity had just taken its first step beyond the prison of conventional physics. The key had been hidden in plain sight, encoded in a paradox so elegant it almost mocked us. You cannot go faster than light, but space can. Those 7 words changed everything. We hadn't broken the rules. We'd simply learned to play a different game. In a sterile lab bathed in blue light, surrounded by instruments thrumming with restrained energy, history shifted in silence. The scientists stood frozen, watching data spill across their monitors, afraid that even breathing might disrupt the miracle. What they had built was not merely a propulsion system. It was a message, proof that the universe had been keeping secrets, and humanity had finally learned how to ask the right questions. Einstein didn't just give us relativity. He gave us a cage. In 1905, he defined the cosmic law. Nothing with mass could reach the speed of light, 299,792,458 meters per second. It wasn't a suggestion or a challenge. It was the architecture of reality itself. As objects approached light speed, their mass would spiral toward infinity, demanding infinite energy. For a century, no one questioned it. We accepted it as truth, the unbreakable geometry of existence. But acceptance has never silenced curiosity. Writers like Clarke and Asimov imagined starships bending the fabric of reality. Warp drives, hyperspace, folded universes. These weren't just fantasies. They were hypotheses cloaked in narrative, equations disguised as adventure. Buried in those stories were seeds of possibility waiting for the right minds to tend them. NASA had already redefined the possible. Moon landings, interplanetary probes, telescopes peering to the edge of time. Each triumph stretched the limits of human reach. But those were steps within the known rules. This was something else, a rewrite of the rules themselves. When the press gathered at NASA's Jet Propulsion Laboratory that morning, they expected updates on rovers and budgets. Instead, they walked into a moment that would divide history into before and after. The air felt heavy, charged with quiet enormity. Senior scientists, normally composed, sat with reverence, as if bearing witness to something divine. When Dr. Sarah Chun, Director of Advanced Propulsion, began speaking, her voice faltered, trembling under the weight of revelation. We have successfully created and tested a propulsion system capable of achieving effective velocities at or near the speed of light. The silence that followed wasn't confusion. It was the sound of reality reorganizing itself. Then came the details. The prototype had vanished from one point in space and reappeared at another, covering a distance that should have taken minutes, instantly. The engineers who had launched humanity's dreams into the void now sat in tears, whispering, "We did it." When asked how, Dr. Chen only smiled and said, "We didn't break physics. We learned to dance with it." The answer lay in the very fabric of space-time. Einstein had shown us that space and time are one, flexible, elastic, shaped by mass and energy. Massive objects bend this fabric, creating gravity. But what if we could bend it deliberately? Compress space in front, expand it behind, create a wave that moves, carrying a ship inside a bubble of normal space. The ship wouldn't exceed light speed. Space itself would move. In 1994, Miguel Alcubierre proposed exactly that, the warp drive. The math worked, but the energy demands were impossible, requiring exotic matter with negative energy density equal to the mass of Jupiter. It remained theory until NASA made it real. The breakthrough wasn't in brute power, but in precision. They learned to shape a localized bubble of warped space, not across light years, but within meters, controllable, stable, and safe. Inside, physics behaved normally. Outside, space bent like a wave around a stone. The ship didn't move through space. It moved space itself. The first test took place at 3:47 a.m. in a sealed Nevada facility. A cylindrical craft, barely larger than a refrigerator, hovered in a magnetic field. When the warp field engaged, it didn't accelerate. It simply ceased to exist, then appeared 100 meters away. 17 repetitions. 17 successes. Each one a miracle. The project had begun years earlier under code names like quantum field analysis and high-energy propulsion research. The funding was buried deep in defense budgets. Officially, it didn't exist. Unofficially, it was called Genesis, not because it was about creation, but because it marked a new beginning. The team worked in silence and secrecy, driven by obsession. Careers dissolved, marriages ended, health deteriorated, but they pressed on, because some problems demand everything. The true breakthrough came when they solved the negative energy dilemma. Instead of conjuring impossible exotic matter, they learned to manipulate quantum vacuum fluctuations, the constant birth and death of particle-antiparticle pairs in empty space. By controlling those fluctuations, they generated regions of effective negative energy density without breaking physics. When the first warp bubble held for more than a microsecond, the team fell to the floor and wept. Project Genesis had succeeded. The system they built was called the Quantum Flux Field Drive, or QFD. It didn't push or burn. It sculpted. It shaped the geometry of space-time itself. The drive created a bubble 50 meters wide where space remained flat inside and curved outside, expanding and contracting in a precisely controlled wave. The result was motion without motion. Movement through geometry rather than distance. The heart of the QFD was the quantum harmonic regulator, an AI-driven mechanism making thousands of corrections per second. Maintaining a warp bubble was like balancing on the edge of mathematics itself. One error could collapse space, or worse, twist it. The regulator made perfection possible. When the drive activated, witnesses described a halo of blue-white light, the eerie glow of Cherenkov radiation shimmering around the craft. Then it simply disappeared. No sound, no flash, just absence. And somewhere else, it reappeared. Identical, untouched. Passengers would feel nothing. No acceleration, no pressure, no motion. Because there was none. Space moved. It did not. The world changed overnight. NASA rewrote its mission statement. We no longer escape gravity. We sculpt it. Humanity had broken its final chain. Probes to Proxima Centauri, once 40,000-year journeys, were now feasible within years. Mars became a stepping stone, not a frontier. Light years turned from barriers into routes. Space was no longer measured in distance, but in geometry. We used to ask how far, one scientist said. Now we ask how curved. Einstein, it turned out, had never been wrong. The speed of light remained absolute for anything moving through space. But there had never been a rule against space itself moving faster than light. The universe had done it before, during inflation near black holes. NASA had simply learned to replicate it. Relativity still stood, but its scope had expanded. Physics textbooks were rewritten. Universities added courses in warp field mechanics. Humanity's concept of travel evolved from speed to structure, from force to form. The ship didn't traverse distance, it redefined it. In the months that followed, new questions emerged: ethical, philosophical, existential. In NASA's newly formed Office of Spacetime Ethics, physicists and philosophers gathered. The issue wasn't whether we could use the technology we already had, but whether we should. Every warp event sent ripples through the cosmic fabric. Tiny, imperceptible distortions. But what happens when thousands of ships warp daily? Could reality itself wear thin? Could the universe remember? One physicist described it as geometric fatigue. Another, more poetically, said, every warp tears a thread and mends it again. What if one day, space refuses to heal? The room fell silent. They had built a miracle. But miracles always come with weight. The cultural shift was immediate. Children drew warp ships instead of rockets. Artists sculpted curved light. Philosophers debated the ethics of manipulating the cosmos. The stars, once symbols of distance, became coordinates, reachable, tangible, real. Humanity's loneliness gave way to anticipation. Pilots trained not in navigation, but in geometry. Journeys weren't measured in miles, but in cycles. How many expansions and compressions it would take to fold the universe around them. For centuries, progress meant speed. Faster horses, faster rockets. But the QFD revealed the truth. The universe was never about speed. It was about shape, about understanding how reality bends, flows, and breathes. We hadn't conquered light. We had harmonized with it. In the quiet NASA lab where it all began, now a designated historical site, the hum of the warp field generators still echoes at night, a low vibration that feels less like sound and more like presence. Through the glass of the observation chamber, the dormant prototype sits beneath the dome, stars shining above it. And in its reflection, you see both the machine and the cosmos, past and future, side by side. And in that reflection, the truth becomes clear. The universe's gates were never locked. We just needed to stop trying to break them and learn how to step through. The journey to the stars was never about reaching them. It was about understanding that in a curved universe, reaching and arriving are the same act. The age of lightspeed travel hadn't begun. The age of geometric navigation had arrived, and with it, humanity's true awakening among the stars.